Model how independent decision makers interact. Game theory uses a framework called a strategic game. It requires three ingredients: a set of players, a set of available actions for each player, and preference relations that map those actions to specific real-numbered payoff. The objective in these models is to locate a Nash equilibrium. A Nash equilibrium is a specific profile of actions where no individual player can increase their payoff by deviating, assuming all other players keep their actions the same. Consider a strictly competitive environment, like the classic game matching pennies. Two players face a strict binary choice: reveal a penny as heads or reveal it as tail. The rules are rigid. Player 1 wins the stakes if both coins show the same side. Player 2 wins if the coins show opposite sides. If player 1 chooses heads, player 2's best response is tails. If player 2 plays tails, player 1's best response shifts to tails. The advantage constantly chases its own tail, meaning the players will never settle into an intersection of pure deterministic strategies. Without a predictable steady state, this strictly competitive system remains mathematically chaotic. To locate stability in these environments, the rules governing how players make decisions have to be adjusted. The formal resolution to the matching pennies problem is a concept called the mixed extension. Instead of choosing a single definitive action, players adopt a continuous probability distribution over all their available actions. This is a geometric visualization of Kakutani's fixed-point theorem. Transitioning from discrete choices to continuous probabilities creates what mathematicians call a compact bounded set that is completely filled in without any holes. Because of these topological properties, Proposition 33.1 states that every finite strategic game is guaranteed to have at least one mixed strategy Nash equilibrium. But this mathematical guarantee creates a paradox, formalized in Lemma 33. 33, Part 2. For any mixed strategy to actually qualify as an equilibrium, every pure strategy within its support must yield the exact same expected payoff. The support of a distribution simply refers to the specific actions that are assigned a probability greater than 0. The behavioral implication of this is quite severe. A player choosing to play heads 50% of the time and tails 50% of the time only does so if playing heads 100% of the time yields the exact same expected utility. The math provides a steady state, but it requires a perfectly optimizing agent to meticulously randomize their behavior between options they care equally about. It leaves us questioning why a rational actor would exert the effort to maintain this precise randomness when any other mixture yields the exact same result. This is a minimalist matrix for a coordination game known as Bach or Stravinsky. Two players want to attend a concert together, but they disagree on which composer to see, creating two pure Nash equilibria where they coordinate successfully, but yield different payoffs for each individual. This Cartesian plane maps continuous probabilities to locate the mixed equilibrium. Player 1's dashed response line features flat segments representing absolute mathematical indifference, where every probability mixture yields the identical payoff. We add player 2's solid line, and the system stabilizes at their exact intersection. At this precise coordinate, player 1 expects the identical payoff, whether she plays Bach, Stravinsky, or any continuous probability mixture in between. This equilibrium point mathematically exists. Yet players have strictly zero incentive to adhere to the precise probabilities, because deviating doesn't lower their payoff. The standard defense, found in introductory textbooks, suggests that players deliberately flip weighted coins to remain unpredictable to their opponents. However, in a single-shot game with no repeated interactions, this defense collapses. Attempting to outwit or guess an opponent's move is a deliberate, highly calculated psychological operation, not an exercise in random coin flipping. Game theorists Martin Osborne and Ariel Rubinstein argue that treating mixed strategies as deliberate randomness forces players to base their optimization on external factors completely irrelevant to their actual payoffs, like their mood or the weather. A system reliant on perfectly indifferent actors, acting as random number generators, is incredibly fragile. Any slight change in those irrelevant external variables causes the steady state to disintegrate. If the foundational steady state of game theory relies on players acting randomly while being perfectly indifferent, our model of rationality is incomplete. In 1973, economist John Harsanyi published a theorem that provided a formal resolution to this indifference paradox. To understand his solution, you have to completely discard the idea of deliberate randomization or coin flipping. Harsani introduced the concept of the perturbed game. Instead of viewing a game as a serial-static matrix, he redefined it as a frequently occurring situation subject to microscopic variation. Mathematically, a player's payoff is no longer a fixed value. It becomes that fixed value plus an epsilon variable, representing a small random variation. These epsilon variables represent tiny, continuous fluctuations in preference, turning a flat matrix into a shifting topographical landscape. The critical rule of this perturbed game is that the exact realization of the epsilon variable is private information, known only to the individual player. This creates a Bayesian game, where players are uncertain about the precise characteristics or payoffs of the other participants. By injecting microscopic, privately known noise into the environment, Harsani's model mathematically breaks the unnatural symmetry of strict indifference. This diagram shows a stark cross-section of a payoff threshold during a single iteration of the perturbed game. Watch as two parallel lines representing perfectly indifferent payoffs begin diverging when a microscopic epsilon value is applied to one of them. Because this epsilon value is drawn from a continuous distribution, the probability of it being exactly zero is zero. Absolute indifference vanishes. For almost any realization of this microscopic noise, one specific pure strategy will cross the threshold and become strictly optimal for that player. In this perturbed state, they are not guessing. They are not randomizing. They are making a ruthless deterministic choice based entirely on their own private data. At the micro level, there is no mixed strategy. Every individual player optimizes perfectly and plays a pure strategy based on knowledge, invisible to their opponent. Shift perspective from the single player's private threshold to the aggregate population level, where a mass of players are all drawing different private epsilon values. Harsani's theorem states that, as the size of these perturbations approaches zero, the sequence of strict pure strategy choices converges perfectly. This smooth convergence of choices directly creates the exact mathematical probability distribution that we originally defined, F and infinity strategy. The 2/3 and 1/3 probabilities from our earlier Bach or Stravinsky game are simply macro-level summaries of these varying microscopic deterministic choices across the population. A mixed strategy equilibrium is not a fragile state of indifferent actors flipping coins. It is the macroscopic footprint of a population making strict, rational choices, driven by the unobserved, microscopic complexities of reality.